Atomic Structure and Quantitative Chemistry. That's Unit C2, Sections 3.1 and 3.3. Now I know that for some of you this will be a really strong section, but it will fill others with dread. Even if you don't like maths and find it very hard, there are parts of this section that you can score really well in. This builds on the work that you did at the start of Unit C1, so if you haven't revised that yet, you might want to go back and do that first. In this unit, we will look at subatomic particles, isotopes, relative atomic and formula masses, and moles. Nope, not the mammals, the way of measuring numbers of atoms. Remember the subatomic particles covered in C1? This time we're going to concentrate on the masses of these particles. Protons and neutrons weigh the same as far as we're concerned. There's a slight difference, but not enough to notice in any of the work that we're going to do. Electrons have no mass compared to a proton or neutron. Again, they do have a mass, but it's too small to notice in the calculations we're going to be doing. The atomic number is the number of protons, and the mass number is the number of protons and neutrons added together. Those are the heavy particles in an atom. The periodic table shows the mass number for the elements, that's the heavier number at the top, and the atomic number, and that's the smaller number at the bottom. The numbers of protons is the same as the atomic number, in this case 1 for hydrogen and 3 for lithium. The number of neutrons is the mass number minus the atomic number, 0 for hydrogen and 4 for lithium. Finally, the number of electrons is the same as the number of protons in an atom, although that's not true for ions. See the structure and bonding section. Next, we need to look at isotopes. Isotopes are atoms that have the same number of protons but different numbers of neutrons, and should not be confused with a Springfield baseball team. This means that they have the same atomic number but different mass numbers. These two atoms are not isotopes. They are just different as they have different numbers of protons. Both these atoms are hydrogen as they have 1 proton each and so the same atomic number. But they have different numbers of neutrons, however, so they have different mass numbers and are different isotopes of hydrogen. If you are asked a question about isotopes and given an example like the hydrogen one here, then do include the mass and atomic numbers in your answer, along with the numbers of protons and neutrons in each atom. Relative atomic mass and relative formula masses are relatively easy to calculate. Atoms are far too light to weigh in any normal way, and the mass in grams or even nanograms would be very small. Instead, we compare the weights of the atoms to each other, and we use a relative scale. It would seem sensible to compare everything to the mass of a hydrogen atom, and this would mean that the relative atomic mass of any atom was the same as its mass number. But instead we compare the mass of an atom to 1/12 of the mass of a carbon-12 atom. As far as we're concerned, this does the same thing, and you don't need to know why we use this scale. The relative atomic mass of an atom is the same as its mass number. Relative formula mass is the same, but for compounds. If you have a covalent compound, it's the mass of one molecule relative to 1/12 of the mass of one atom of carbon-12. If it's ionic, you just use the atoms given in the formula. You end up working both out in the same way anyway. To find the MR of methane, add up the mass of all the atoms in the formula. In this case, 12, and 4 lots of 1 make 16. If it's an ionic compound, you do the same thing. Don't worry about the fact that they're ions. Ions are atoms where the number of electrons have been changed, and as the electrons don't have a significant weight in an atom, the mass of an ion is the same as the mass of the atom. But be careful with brackets. Here, Ca brackets OH close brackets 2 means 1 calcium and 2 lots of OH. If you aren't very good with using brackets on your calculator, then I would suggest writing out the sum as I have shown the first way. Moles, the way of measuring how many atoms you have. Even a billion atoms wouldn't weigh enough to register on a balance in the lab. We need to use a huge number for our groups of atoms if we're going to be able to weigh them. The number chosen was the number of hydrogen atoms that weigh 1 gram. You don't need to know what the number is, just that it's called 1 mole. 1 mole of an element weighs its AR in grams. 1 mole of a compound weighs its MR in grams. Now we need to use these numbers to work out the answers to chemistry problems. Question 3.